So this is going to be, I hope, a shorter than normal review of what we did in class on Monday, May 11th of 2020. We began, this is a unit on acids and bases, and given the coronavirus time that we're in, it'll be a shortened treatment of acids and bases, but at least you will have some introduction to what they're all about. I put some background reading that I'd like for you to do on the website. It's right over here, acid-base background reading. And if you click on that, you'll see a section of our little used textbook. And it's also on our main website, but you can look at that later. Anyway, this link is in the homework section, and we spent some time talking about acids and bases. And acids have these characteristics. You can read through this, but they are electrolytes, which means they conduct current. They taste sour. You know you've tasted lemons. You might say, well, oranges have acids in them and they don't taste sour, but remember, oranges have sugar naturally. And if you ever taste an orange that's not ripe, it'll taste sour. And you know the vinegar is sour, and sour candies that we all kind of like they're just sour. The candies have a little sugar in them, which helps. Acids change color in acid-base indicators. You'll remember at the beginning of the year that I had someone blow into a pink liquid and it turned clear. That was phenolphthalein. That's an acid-base indicator. The most famous one is litmus. Litmus is turns red if it's acid. It turns base if it's blue. And it changes color at pH 7. You see over here on the right side. And if it's red, it's acidic, which means less than 7. And if it's blue, it's basic, which means more than 7. So less than 7, acid. Greater than 7, base. Litmus is sometimes used in politics as a way to describe a candidate or a position on an issue. It's famous for being it's either acid or it's base. It's either this or it's that. It's yes or it's no. So it's a litmus test in politics is a way for you to get an opinion of where a candidate is going to stand on based on his response to certain issues, like maybe abortion. I'm pro-life or I'm pro-choice. It would be kind of a litmus test. All right. Acids react with metals to make hydrogen, and when they react with bases, they make a salt and water. So acids react with bases to make a salt and water. So that's all I'm going to say about acids. Bases, a little section on bases. Milk of magnesia is a famous base. Bases taste bitter. So they're also make ions in solution. They're electrolytes. They taste bitter. If you've ever had your mouth washed out with soap, you're familiar with this. When you use bad language, your mom washes your mouth out with soap. I don't know if that happens so much anymore, but it used to happen back when I was a kid. Kids would use bad language and your mom would wash their mouth out with soap. And they change the color of indicators too. Once again, litmus turns blue in base and red in atlas. That's litmus, red in acid. Bases don't react with metals like acids do, and they also are neutralized by acids to make a salt and water. This would be a basic solution of phenolphthalein. If you blow into that long enough, it'll turn clear because your carbon dioxide will make it more acidic, and it'll go clear. All right, if you've ever taken Tums, that's a base. Drain cleaner, Drano, is a base. So anyway, you can read through that, little characteristics of bases. All right, then we looked at theories of acids and bases. The first one was the Arrhenius theory. So the Arrhenius theory, you can read, I won't point all this stuff out. The Arrhenius theory is basically this. Acids have an H in front, and when they put them in solution, they separate and you get H plus and CO minus. Now we've said normally in our class that ionic things dissociate like this. They come apart when they dissolve, and molecular things don't. But acids are an exception to that. Acids are molecular things that act ionic in that they make ions when you put them in solution. It's the H that comes off. You'll notice that not everything that has an H in it has an H that'll come off. Like CH4, natural gas, is not acidic. It doesn't have an H that is able to be released. And the reason for that is carbon is not electronegative enough to pull the electrons away from the hydrogen. So the hydrogen is not exposed and it can't leave. Down in a situation like this oxygen is very electronegative and it pulls the electrons away from the hydrogen so the hydrogen can be lost. All right, so Arrhenius would say that an acid has an H in front and provides hydrogen ions. The base theory for Arrhenius would be that bases have an OH at the end, like all of these. All right? And when you put them in solution, the OH comes off like that. So bases have this ion, the OH minus. All right, so Arrhenius, these are the class notes. Acids, H in front, like H plus makes H plus plus Cl minus. Base has an OH at the end. Then, so we looked at what are acids and what are bases. So if you look at KOH, it's got an OH at the end, it's a base. HNO3 has an H in the front, it's an acid. NaOH, OH at the end, it's a base. Acid in front, OH at the end. Acid has an H in front, OH at the end here makes this a base, and HBr makes this an acid. Now we also spent a minute talking about monoprotic or diprotic acids. Monoprotic, diprotic, polyprotic, triprotic are words that we use sometimes to talk about acids. So if we look at this chart of acids, the red one would be monoprotic because it only has one hydrogen to come off. So would nitric acid be monoprotic, only one hydrogen here to come off. Sulfuric acid would be diprotic. It's polyprotic, but in this case it's di because there's two hydrogens. And H3PO4 would be polyprotic, but that would be triprotic. See down here as H3PO4. This one looks like it might be polyprotic, but really there's only one H that can come off. Remember, the H's that are attached to the carbon can't get away because carbon's not electronegative enough to pull the electrons away from the hydrogen. So this is a monoprotic acid. Only that H comes off. And hypochlorous would be monoprotic. All right. So that's the Arrhenius section. Next thing we talked about was the Bronsted-Lowry, what's called the Bronsted-Lowry definition of an acid. And they say that an acid is a proton donor and a base is a proton acceptor. So let's take a look at that. I'm going to go to the Arrhenius. There's a picture in the Arrhenius section that lends itself better to the Bronsted-Lowry theory, and that's this one here. So if you look at this molecule, you've got a gray H or a grayish or a whitish gray base. Let me start that again. Look at this molecule. This part, the white part, is an H, and the green part is the Cl. So when they react with water, when this reacts with water, this gray comes over here and sticks onto the water. See it right here? Now we've got an H3O and a Cl minus. Now, Bronsted and Lowry say, well, this was not an H that transferred, it was just a proton. And if you think about it, here's a picture of a hydrogen over on the right. It's a hydrogen atom, only has one proton and one electron. So if that electron gets left with the chlorine, see I circled it here, all that really got transferred was this proton. So this electron was left with the chlorine. The only thing that really got transferred was the proton. It went over here to make H3O. So an acid is a proton donor. This guy donates a proton to the water. Now Bronsted and Lowry would say, well, so if an acid donates a proton, then a base must accept a proton. And so therefore they'd call the water a base. You might say that the definition is getting broader. Now Arrhenius knows this happens, but he just ignores this water. So he just leaves the water out of this, and so all he writes in is the H+. So the Arrhenius definition says, I've got to have this H+. Bronsted and Lowry is a little bit more inclusive, and we'll see why a little later. Now, if we go then to the Bronsted and Lowry definition, they point out that often things that have exposed electrons can accept protons. So then a base becomes more than just having an OH at the end. Like over here it said base has an OH at the end. They'd say, no, base is anything that can accept a proton. So proton acceptor. All right, so Bronsted acid is a molecular ion, or ion, could be an ion that is acting like an acid, that donates a hydrogen ion. And same thing for a base, it receives a hydrogen ion, commonly referred to as a proton. The hydrogen ion is commonly referred to as a proton. So acids and bases are proton donor acceptors. Anyway, okay, moving on. Oh, there's a, let's look at the reactions now. What do we call the things that react? That's the reaction section. So in a Bronsted-Lowry acid-base reaction, something acts like a base and something acts like an acid. So in this case, you see the water was H2O, became OH minus. So it donated an H to the NH3, which became NH4. So if an acid's a proton donor, in this case, water is an acid. And the NH3 is a base. Down here, water accepts a proton. So it acts like a base. So in class, I forgot to mention this term, but this is a term that you should know. Amphoteric means that you can either act like an acid or like a base, depending on if you're donating or accepting. So something that goes both ways is amphoteric. All right, conjugate acids and conjugate bases are the conjugates are what act like an acid going from right to left. So if you look over here on the right, the H3O, if I was going back here, would donate a proton and go to the HCl, or excuse me, to the H2O. So this would be the acid, conjugate acid, and that's the base. This would be the conjugate base because it's going to accept the proton from this as you go from right to left. Technically, if you read the definition, a conjugate acid is a particle produced when a base accepts a proton. So here's your base. It accepts a proton, made the conjugate acid. Here's the acid. It donates a proton, becomes a conjugate base. That's this other definition over here. All right, so these are called conjugate acid-base pairs. Let's take a quick look at a video explaining, or an activity explaining that. So we'll do a couple of these. All right, so if you click on the conjugate acid, it wants us to do that. Conjugates are going to be on the right side. So what's going to go donate a proton going from right to left? If you said NH4, you know that would be correct because the H goes over here and now it makes H2O. Instead of one H with an O, now you got two H's. Okay, what's the conjugate acid? Same thing, the H goes to the S. The base is on, this is not a conjugate, so it's a regular base, it'll be on this side. So what what accepts the proton on the left side? Looks like it'll be the Cl. Okay, and if you keep going, I'll do another one. So you can do this on your own, but what's the conjugate base? What's going to accept the proton from this? Looks to make, in other words, if this turns into that, donated a proton, what accepted it would be that. Click on the acid. What's going to donate the proton between these two things? The HSO4 donates and so on. So I'll let you work with that. All right, now moving back to the to where we were. That's what I want to say about Bronsted and Lowry acids and bases. All right, the Lewis acid-base theory. It says that an acid is an electron pair acceptor and a base is an electron pair donor. So it gets more broad. See how the diagram, you're getting more inclusive. So in this case, this H is donated to that, so that would be, this is an acid being donated to a base. Or the base is actually donating a pair of electrons to the H. So Lewis would say, no, an acid's not a proton donor, it's an electron pair acceptor. See over here? So that's a broader definition because now, if you look at this reaction, see the BF3 could accept this electron pair because there's an open spot creating this bond. So that makes the BF3 an acid according to Lewis, and the base would be the NH3. So it's just a broader definition. This one's used in organic chemistry. We tend to, this is an inorganic class, so we will use the Bronsted-Lowry definition that I have circled over here. But this is a nice little table that summarizes the three acid-base definitions. All right. Now, going back here. I wanted to take a look at the self-ionization of water. We're going to get into this tomorrow. So I wrote an equation for that. Looks like that. Water actually reacts with itself. Now you can read this, but I'm going to summarize it, what it says. It So water reacts with itself. When it does, it makes hydronium and hydroxide ions. This H3O, by the way, is called hydronium. I wrote that down here. Or did I? Hydronium, there we go. H3O plus is called hydronium. So you might want to know that term, hydronium. Okay, so this is the equilibrium expression for that, but something I haven't talked to you about is that you cannot change the concentration of liquids or solids. Let me say that again. Liquids or solids, like these liquids, cannot have their concentration changed. So since they're constant, I mean, think about it. Can you smush a liquid together? Can you smush a solid together? So you can't change their concentrations. You can change gases because you can make them get smaller or bigger. We know about that. And for liquid things that are dissolved in water, I mean, aqueous things, you can dissolve a little bit of sugar or a lot of sugar in the same amount of water. So you can change the concentration, but you can't change liquids or solids. So therefore, we don't include them in equilibrium constants, and I move them over here. Both of them are constants. So that's a constant concentration. That's the equilibrium constant. So we come up with a new constant that looks like this, called the ion product of water. And that value is 1 times 10 to the negative 14th. We will talk more about that tomorrow. So remember, no liquids or solids in equilibrium expressions. Why not? Because concentrations of liquids and solids are relatively constant. You can't really change them. All right. So if in any solution, water-based solution, the hydronium ion times the hydroxide ion concentration will always equal this number. So that's important for tomorrow's class. All right, and then the last thing I mentioned today in class was neutralization reactions, and I've already mentioned them once, so I was just going to remind you of what I said earlier, essentially. There we go. So this, in blue here, is a typical neutralization reaction. I want you to read about the net reactions, but for right now, the most important thing that you know is that if you combine an acid with a base, you always get a salt and water. So this is table salt. So if the acid is HCl plus NaOH, you're going to get table salt and water. But if the acid was HNO3 plus water, or excuse me, plus NaOH, you would get NaNO3 plus water. And NaO3 is a salt, and this is water. So the technical definition of a salt is the positive ion from a base and the negative ion, and you can see I didn't draw the arrow very well, but that's the positive ion, the negative ion from an acid. So positive ion from a base and a negative ion from an acid. The definition of a salt. So you can have, you're starting to think, wait a minute, that means salt's more than just NaCl. And the answer to that is yes. There are many, 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 many different kinds of salts. Some of them are good for you, some of them are not. And NaCl, well, we use it anyway, whether it's good for us or not, but NaCl is the most common. All right, so summary of what we did today. That was quick, but maybe not as quick as I intended to be. We started by talking about indicators, just introducing you to acids and bases and litmus. We looked at 3 definitions of acids: Arrhenius, Bronsted, Lowry, and Lewis. We then looked at water reacting with itself and developed this constant, which we're going to come back to tomorrow. And we talked briefly about acid and base reactions. They always make a salt plus water.